Well, I'm Peter Sonak from the School of Math, and I'm welcoming you all on this special day, celebration of Women in Mathematics Day. It is also the day that is Mariam Mirzakhani's birthday, so I think that's coordinated that way. And we at the Institute have been celebrating this day for the last few years on this occasion, and it's celebrated around the world. And we're part of many people celebrating Women in Math today. And for our speaker today, we have our own Sarah Peluse, who's a Veblen instructor, who's a member both at the Institute and at the university for the last few years. She got a PhD at Stanford with Soundararajan and has shot up to the top very quickly, winning numerous prizes, most recently the Koenig Prize of the Society of Industrial and Applied Mathematics for up-and-coming stars. And she's a winner of the Breakthrough Prize, named after Mirzakhani, the Mirzakhani Prize earlier this year. Sarah works in additive combinatorics and number theory, where she's made a number of remarkable contributions, including effective bounds in the polynomial Szemer theorem over finite fields and also over the integers. She's made a remarkable breakthrough on an old problem of perfect difference sets in additive, just that Z mod NZ additive number theory problem, where the problem stood still for a long time, and she made a big progress in that direction. And also in the problem of divisibilities of entries in the character table of the symmetric group. A problem that I understood from your lecture was motivated by numerical inspection quite recently in Sarah, and nobody had apparently any idea how to tackle this problem. And Sarah immediately recognized how to prove the divisibility properties, and has continued with numerous works of that type. And the title of her talk today, which will be, I think, around the polynomial Szemer or effective bounds for Szemer for L-shaped configurations. It's a tremendous pleasure to have Sarah here and give this talk for us. Let's maybe welcome her.
Okay, so thanks for the introduction and the opportunity to speak. So the starting point of my talk is Szemer's famous theorem on arithmetic progressions. I think everyone has seen me start a talk this way already here, but to remind you, the Szemer's theorem which was proven in 1975 and answered or confirmed it 1936 conjecture of Erdős and Turan states that any subset of the natural numbers having positive upper density must contain arbitrarily long, non-trivial arithmetic progressions. Okay, so that means configuration is form x plus y. I'll go up to x plus, if you want it to be length k minus 1 plus y. And so positive upper density means that your set has positive density in arbitrarily long initial intervals of integers. So the lim sup, n tends to infinity, of the density of your set in the first n integers is positive. And non-trivial means that y can't be 0, so that this is like actually an interesting theorem. So this formulation is Szemer's theorem. It's equivalent just by compactness to the following formulation, that if A is a subset of the first n integers, which I'll now denote with these square brackets around n. And so if A is a subset of first n integers, it has no non-trivial k-term arithmetic progressions, then size of A is little o of the size of the whole interval. And it's a central open problem in combinatorial number theory and additive combinatorics to determine the best possible bounds for this little o event term. So in other words, to determine what is the size of the largest subset of the first 9 integers without any non-trivial k-term arithmetic progression. So we're interested in this question, not just because it's asking for like, what's the best possible bound you can get in this big famous theorem, but because Erdős was interested in this question. So it's an old conjecture of Erdős. I think it dates back to the 40s. That if S is a subset of the natural numbers, and the sum of the reciprocals of all the elements of S diverges, then S has arbitrarily long arithmetic progressions. Okay, so how is this related to this? Well, upper density and sums of reciprocals diverging are both like 2 measures of the size of a set. So this conjecture is saying, well, if your set is big enough, then it should contain arbitrarily long arithmetic progressions. So these notions of like largeness, they're not quite like equivalent, but they're roughly equivalent. And if you were able to prove bounds a little bit better than like n over log n in Szemer's theorem, then you would prove Erdős's conjecture. Okay, so then why did Erdős state it in this way? So it was a much older, like I think like hundreds of years old folklore conjecture that the primes contain arbitrarily long arithmetic progressions, and the sums of reciprocals of the primes diverges. And so Erdős was interested in, well, if the primes contain arbitrarily long arithmetic progressions, is this because the primes are just sufficiently dense, or is it something like special about the primes? So this conjecture on primes and arithmetic progressions is now a theorem. It's the famous Green-Tau theorem, and they proved it not by proving like Erdős's conjecture, but by exploiting the pseudo-randomness properties of the primes. So this conjecture of Erdős is still wide open. So maybe I'll tell you kind of what's known towards this open question. So Szemer proved his theorem by some like complicated combinatorial argument where he introduced his now famous regularity lemma for graphs. And you can extract bounds like from Szemer's proof, but they're extremely poor. Like the savings over just the trivial bound of this n is like inverse Ackermann. So think of like worse than the inverse Cauchy function when k is sufficiently large. But almost for more than 20 years before Szemer proved his theorem, Roth proved the k equals 3 case. So 3-term arithmetic progressions. A subset lacking 3-term arithmetic progressions smaller than n over log n. And he did this using Fourier analysis. And all of quantitative improvements on Roth's argument in the integer setting have been just more and more elaborate, like variations of Roth's argument. And now, it's about 2 years ago now, Tom Blue and Olaf Sisask, 2020, showed that A has no non-trivial 3-term arithmetic progressions, size of A, is bounded by n over log n to some power greater than 1. So they're the first ones to break through this like logarithmic barrier, and like thanks to them, we now know the first non-trivial case of Erdős's conjecture. Okay. So for longer progressions,
So should I read that we know the conjecture where we replace arbitrarily long by of length 3?
yes, yes. Okay. So for longer progressions, no kind of reasonable quantitative bounds were known until work of Gowers in 1998 for k equals 4, and 2001 k for all k. Showed that if A has no non-trivial k-term unifying progressions, then the size of A bounded by n over log n to some power that depends on k. So I think it's 2 to the negative 2 to the k plus 9. And so Gowers did this using and initiating the study of higher order Fourier analysis. Which I'm not going to tell you what this is, because I told you in like my members colloquium, and there also won't be time. So I'll mention this a bit in my talk, but not too much, hopefully. So Gowers' bounds in Szemer's theorem are still the best when k is at least 5. But Green and Tau have proved bounds of the form n over log n to some like small power for sets lacking length 4 arithmetic progressions. So I've mentioned now like 2 proofs of Szemer's theorem. So I've said there's Szemer's original proof, and then there's Gowers' proof using higher order Fourier analysis. Another very important proof is Furstenberg's proof via ergodic theory, where he introduces now famous correspondence principle. And Furstenberg's proof is important, like not because it gives quantitative bounds, because it doesn't, but because his method has so far been like the most flexible of the methods used to prove Szemer's theorem. Has led to like some very broad generalizations. The original result, one of these is the multidimensional Szemer theorem of Furstenberg and Katz-Nelson. I think this was just like a year later. Okay, so it states that if we let S be a finite non-empty subset of z to the d, and if A is a subset of n by n by n by n d-dimensional integer grid that has no non-trivial homothetic copies of S. So sets of the form a translate of some dilation of S. Then the size of S, sorry, no, the size of A is little o of the trivial bound n to the d. Get Szemer's original theorem back by taking d to be 1 and S to be 0 up to k minus 1. So you could think of this theorem as saying, like, if you like had a light bright as a kid, you draw like whatever picture you want on your light bright.
Can you tell us what a light bright is? For those of us
Oh, do they not have them in Canada?
No.
So it's like this. It's a black. It's a finite, like say n by m integer grid, and
yeah, you pin the little.
yeah, you put the things in, and then the different colored things. Colors aren't part of this, but and then the light makes a picture. So you draw whatever picture you want in your light bright, like a dog or something, and then at any like infinite light bright where there are sufficiently many pegs, a copy of your dog will appear. That's great. It's like a visual theorem, and usually I don't get to draw pictures in talks. So it's a very difficult generalization of the problem of proving quantitative bounds in Szemer's original theorem to prove quantitative bounds in the Furstenberg-Katz-Nelson theorem. So I have this question stated for some specific sets S, kind of in like pretty old papers in combinatorics, but I think the question of proving quantitative version of this in general is first stated by Gowers. So we want this open problem. Prove a version of the Furstenberg-Katz-Nelson theorem with reasonable quantitative bounds.
Gauss, the dependence on K is an exponent in the implied constant, I'm sure, right?
Wait, are you saying?
In Gauss, there's a statement there that
Are you saying there should be a big O sub K?
I assume so.
Oh yeah, probably, because it has to be big enough.
I'm just because I'm trying to imagine what S here, you know.
Oh, yeah. So then there should also be right there. So by reasonable, I mean a savings over the trivial bound of n to the d that grows at least as fast as like a finite number of iterated logs. We don't want anything like inverse Tower or Ackermann type, because there is not just Furstenberg and Katz-Nelson's proof of this result. There are also now several proofs using hypergraph regularity that give bounds of like a similar strength, like an inverse Ackermann savings as Szemer's original proof. So this problem is like very, very, very hard. So it's so hard that we only know reasonable bounds for one genuinely multidimensional configuration. So if you take S to all lie on some line, then you can just, like by an averaging argument, find some line on which your set A has positive density and then just apply like the one-dimensional version of Szemer's theorem. And the only S for which where all the points don't lie on a line, for which we have bounds, are when S is subset of Z2, 0, 0, 0, 1, 1, 0. Okay, so you draw these in Z2, it looks like this. Okay, so this configuration is called a corner. So for corners, this is due to Shkredoff. And so he proved that if A is a subset of the n by n integer grid, then it has no non-trivial homothetic copies of this, so no corners. Then A is n over log n to some power. Oh, now I've gotten myself in trouble. This would be more efficient. Okay, so I didn't tell you what higher order Fourier analysis is, but I'll say basically the reason why this open problem is so hard is because we would need a multidimensional version of higher order Fourier analysis, and no one knows how to do that. even though I think lots of smart people have thought like really hard about, I guess like what this might look like, or like attempted to prove some result in it. So yeah, so as I said, the only genuinely multidimensional configuration for which we have quantitative bounds are these corners. So then you would think like, what's next? Like we should do something with 4 points. Because so if you have like a 3-point configuration in like higher dimensions, you can just do some linear transformation to get it to look like a corner in some plane, and then just like use the result for corners in 2 dimensions to prove bounds. And okay, if I was presented with this, I would say the 2 most natural 4-point configurations to look at be to add points to the corners. So we have a corner, and then we add the 4th vertex, the square, and we get axis line squares. And no one knows how to prove quantitative bounds for sets lacking axis line squares. And again, if you have a corner, you could add a 4th point in a 3rd dimension, get 3-dimensional corners. And no one knows how to prove quantitative bounds for sets lacking 3-dimensional corners. And basically, if you try and study these 2 configurations, you run into a problem in multidimensional higher order Fourier analysis that no one knows how to solve. And a toy version of this problem is to classify approximate cocycles. So here are approximate 2 cocycles in group cohomology. Okay, so this problem is to classify functions from, it could be on any abelian group actually. So say G cross G to G, such that F satisfies the 2 cocycle equation like a delta proportion of the time. We can think of delta as like 0.0001. I'm about to check my notes to get the signs right. So that this equation holds for at least a delta proportion of triples X, Y, and Z, all in G. But yeah, so no one knows how to do this.
Can you remind me what's known about primes in multi-dimensions?
So a version of the green tau theorem is known in prime grids like P cross P. And there are actually like 3 proofs of this, or at least 3. And the simplest and nicest is, I think it's by Conlon, Fox, and Zhao. And it's basically, you can use like the green tau theorem to find in like your primes, like arbitrarily long arithmetic progressions, and like a lot of them. And so you can find like big grids in like the primes cross the primes. Then you do some averaging argument to say, if you have some like positive density subset of the primes cross the primes, you can find some like basically some positive density subset of some like big grid. And then you can just apply the multidimensional Szemer theorem in that grid. So you don't actually need to do like any, you can just use the green tau theorem as a black box and Szemer's theorem as a black box, basically. Okay, so this toy problem, Okay, I like advertising it because I think like it seems that no one in additive combinatorics knows how to do this, but like maybe someone who like plays with cocycles more would like know how to do this.
What is G here?
So G is just an abelian group. So G any abelian group. And you can actually take this to be, this doesn't have to be G, it could be, at least in this situation we care about, you could take the torus set of G.
Classify means somehow describe them.
Yeah, so the version of this you get in the one-dimensional setting is to classify what are called approximate polynomials, and these are functions, let's say like from the group to the torus, such that the like discrete derivative of this function is 0 like 1% of the time. And then you can say this must agree, so depending on your group, if your group is like fp to the n as n tends to infinity, then your function must agree with a genuine polynomial, like 0.00001% of the time. And if G is like cyclic group, then F agrees with what's called like a nil polynomial, like 0.001% of the time. So we want some statement like if F is one of these approximate two cocycles, then F agrees with maybe a genuine two cocycle like 0.001% of the time. But turns out that that's not quite true, because you can construct like functions that come from like two cocycles on some like other group that maybe embeds like partially in G. So we don't actually even have like a good conjecture for what like the answer should be. So I hope someone has an idea eventually. Okay, so I guess I'll also mention that these axis line squares are the subject of a conjecture of Ron-Graham. I don't actually know when he conjectured this. But he conjectured that S is a subset of n cross n, and it satisfies the sum of where all the points y of the reciprocal of x squared plus y squared. If this thing diverges, then S contains an axis line square. And more generally, Graham conjectured that if this diverges, then S actually contains an n by m grid for any m. So this is some like two-dimensional generalization of Erdős conjecture. And like Erdős conjecture, like we're kind of very far from proving this. Not even in the, so we wouldn't even know this if you replace the axis line squares with corners, for example. Okay. So my talk today is about a different 4-point configuration, one that I claim we can prove quantitative bounds for sets lacking. And that is, you start with a corner, and this time you add your fourth point above this point to make an L shape. So you have like a 3-term arithmetic progression vertically, and then another point of the same distance horizontally. And I prove bounds for sets lacking this configuration in the finite field model setting. So you can also ask, what's the largest subset of some like finite group that lacks your multidimensional configuration? It turns out in additive combinatorics, people are usually interested in this when your group is a vector space over a finite field where the dimension of the vector space tends to infinity. Because these groups model the integers well. Okay, so I proved, and this has finally appeared on the archive. that if A is a subset of, so sorry, actually, first I want P to be at least 11. And if A is a subset of P to the N plus of P to the N, and it has no L-shaped configurations, so that's configurations of the form XY, y plus C, CY, XY plus 2Z. And then we want C equals 0, so they're non-trivial. So if A lacks non-trivial L-shaped configurations, then size of A is big O of N over a bunch of iterated logs. Oh, sorry, what is N? N is P to the 2N. So the size of this group divided by a bunch of logs of P to the N. We're interested in this as N tends to infinity. Okay, so my first remark is how many logs are here? So I can't promise you that it's any less than 42 trillion. It's less than or equal to, which I hope is this a trillion? Okay. I hope this is a record for like an analytic number theory talk for number of logs.
Is there something special beyond that Gao has got log that defines that as an important threshold? Was it? I mean, if you've got triple log, would that be fine? I mean, what is the sort of the ballpark? What are the benchmarks?
Finite number of logs.
Okay, all right. Okay.
This is good enough. I think people, okay, if you reduce this, I think people would not be interested, like if you could get this down to 1 million. Maybe people will be interested once you get it down to 2 logs.
Yeah, so I'm just, because he seems independent of K, the power of the number of logs is just 2.
Yes, yeah. So that's the important like part.
The power we don't care about.
Okay, so we study things first in the finite field model setting. I mean, people care about it for its own sake, but also because once you get a proof in vector space over finite fields as n tends to infinity, then usually you can transform it into a proof in the integer setting. So there are no serious barriers to like adapting my proof to the integer setting, except that it would be a huge pain. So the proof should adapt. To subsets of the n by n integer grid. Actually, with much better quantitative bounds. You could probably get like 5 iterated logs. And this is because I use a result in higher order for analysis where the bounds are kind of much worse quantitatively in this finite field model setting than they are in the integer setting. Proof should also adapt to prove bounds for sets lacking more general L-shaped configurations. Maybe an L with some really long, like 1 leg. I think it would be harder to do like an L-shaped thing with 2 long legs for some of the same reasons that no one can say anything about axis line squares or 3-dimensional corners. Okay, so I mentioned that this problem is hard because we have no multidimensional analog of higher order for analysis. And I definitely don't claim that I've made sufficient progress to give any hope of proving bounds for sets like in those 2 configurations. But I did have to make a bit of progress in the problem of getting a multidimensional analog of higher order for analysis. So before I start talking about the proof, are there any questions?
Can you tell us a bit about how you got 42
Okay.
trillion?
So the number of logs anything I do adds to this is like less than 10, no matter like how kind of crude and lazy I was in the proof. Because when I like use this result from higher order for analysis, there is like, there's a result that holds for every natural number S. And as S grows, the number of iterated exponentials in this result grows like n factorial or something. And yeah, so it all comes from that. I need this for like 10 or something. Any more questions? I'll start talking about the proof. By first talking about the proof of Shkretov's results, but done in the finite field model setting. So things are simpler. So corners in plus P to the n. So Shkretov proves his result by a density increment argument. So I don't remember if I talked about this sort of argument in my members colloquium, but no matter what, I'll remind you. So Shkretov does is he, okay, I won't have space for this. So if you iterate the lemma that I'm going to write over here now. It'll be a bit vague in its statement. So you let A and B be some large subsets of FP to the n. So you have density alpha and beta respectively. And if now I'm switching the roles of, so S is going to be the subset that we're trying to find corners in, even though before it was like the set that gave us the configurations, the multidimensional Szemer theorem. So if S is a subset of A cross B, density sigma, and it has no non-trivial corners, and there exists large subsets of A and B such that the density of S intersected with A prime cross B prime in A prime cross B prime is significantly larger than sigma. So such that S has density at least sigma plus some constant times sigma squared in A prime cross B prime. And this is all provided that P to the n is sufficiently large in terms of sigma, alpha, and beta. So it's sufficient to take like alpha, beta, sigma to the negative like 10 here. So then what I mean by iterating this is if you start with some subset A of FP to the n cross FP to the n of density sigma with no corners, then you apply this lemma, and either P to the n is small in which case you can just get some bound for sigma in terms of p to the n. Sigma will be like at most like a constant times 1/10, 1 over 1/10, or sorry, 1 over p to the n to the 1/10. Or you get this density increment, and then you can repeat the argument on the product set A prime cross B prime. And at each point, your density increases by a constant times sigma squared. This is some absolute constant, but the density of a set like can't go above 1. So at some point, this will have to fail, and then you will get some bound for S intersected with some product set, and then you can kind of retrace your steps to get a bound for your original set that lacked corners. Okay. So if you believe me that you can prove quantitative corners theorem by iterating this, then I will tell you how to prove this. So to prove this lemma, like in kind of all analytic approaches to Szemer's theorem, we study some weighted averaging operator. So we define lambda sub, supposed to be a corner, of Fj and H to be the average for X, Y, and Z, and Fp to the n of weighted count of corners weighted by, it's supposed to be H. So then if you plug in the indicator function of a set S for each of these functions, you get 1 over p to the 3n times the number of corners in S. So now if you define f sub s to be the mean zero function, the indicator function of S minus this density, then based by using the trilinearity of this average, you get that this weighted count equals weighted count with indicator function of S replaced by f sub s plus the other term. So sigma times weighted count, constant function 1, indicator function and indicator function. And now it's easy to show using the Cauchy-Schwarz inequality that this thing, this whole thing, is at least sigma cubed. And so the sigma cubed is the density of corners you would expect in a random set of density sigma. So if your weighted count of corners differs significantly from this random count, then this term will have to be large to like cancel with this. So in particular, if S has no corners, this thing will be sigma over p to the n. Okay, so if p to the n is sufficiently large, this thing will be like way less than sigma cubed. So this term will have to be, let's say, at least half sigma cubed. So now we want to prove that we can find some density increment under the hypothesis that this thing is large. Well, it turns out that by more Cauchy-Schwarz, if if these are all bounded in absolute value by 1, lambda of f, g, and h is bounded both by the box norm of f, where I'll tell you what this is. So the box norm of f to the 4th power is the average over x, y, x prime, y prime, in f to the n, such that, oh, sorry, of f of x, y, of x, y prime, of x prime, y, x prime, y prime. So it's not obvious that this is a norm. We can show this like by the Cauchy-Schwarz inequality. So this is like a norm that comes up a lot, like in graph theory. It's like a weighted count of C4s in a graph. And it's standard by an averaging argument to show that if f sub s has large box norm, say greater than, okay, whatever we had, sigma cubed over 2, then S has increased density on a product set. Okay. So then obtaining this density increment we want is standard. So the part that like isn't standard about Shkredov's argument is doing this when we're not starting from the point where S is a subset of fp to the n cross fp to the n. So how do we show we can get this density increment when we already have started with S as a subset of a product set? And most of these things I've written down go through, except for this step. So to repeat this, we want to get an inequality like this without losing any factors of the density of A and B. So if we're not careful, you can end up with a loss of these density factors, and you can get a density increment that gets worse as the density of A and B gets smaller, which is not good enough to close the iteration. Here we wanted the density increment to like not depend on the sets A and B. So to repeat this, what we want is that an inequality like this, but weighted by the sets A and B. So we want that if let's say f, g, and h supported on A cross B, and if the ratio of the weighted count weighted by f, g, and h, that weighted by A cross B, want that if this is large, then the box norm localized to A cross B is also large. And it turns out that this implication only holds when your sets A and B are Fourier pseudo-random. Which means that they have no large non-trivial Fourier coefficients. Here we need Fourier pseudorandom.
So just in the additive Fourier analysis in one of the patterns, which
Yeah, so this means that like these are both small. They're all non-trivial additive characters. I guess they're only additive characters here. Okay, but the sets A and B that make up our product set that we're given.
sorry, can I ask a funny question?
Yeah,
Do you use anywhere that FP is a field, or do you just use its additive structure?
you just use, yeah, here you just use its additive structure, but in my argument, you need that it has like, that it's not F2. Like you need,
I know, but
yeah, yeah.
you use at some point some field theory or some polynomials.
Oh. No.
Particular multiplicative structure.
I mean, polynomials do show up.
I mean,
but I guess when
when you get to the integer version, there's no field left, so to speak.
Oh yeah, so what happened? Well, in higher order Fourier analysis, the inverse theorems are simpler in a finite field model setting. Like you get polynomials in 7 nil sequences. So in that sense, like
Oh, okay.
I'm helped a lot by there being like a field.
Okay.
At least, okay, maybe things would still work with nil sequences, but it was just such a huge pain. Like that the ideas of the proof just come through easier in the finite field setting. So the sets A and B that we get from doing this averaging argument to get the density increment, we don't know anything about them aside from that they're large. In particular, like we definitely don't know that they're Fourier pseudorandom. So then Shkredov's kind of key idea was if you restrict to some small like product of affine subspaces, you can actually assume that they're Fourier pseudorandom. So which Shkredov does, he incorporates the pseudo-randomizing step. And then the idea is, okay, so this will be our FP to then cross FP to then. We have our sets A and B here. All we know about them is that they're large. And then Shkredov uses an energy increment argument to kind of like in the proof of Szemer's regularity lemma to partition the space into union of products of affine subspaces on most of which A and B are both large and Fourier pseudorandom. So then we have our set S that we want to find like a density for which we want to find a density increment on some product set. So by an averaging argument, if almost all of these squares are such that A and B are both Fourier pseudorandom and large, then you'll also be able to find one on which S has the basically close to the same density increment as you had before. And then now you can repeat the argument and prove this lemma. Okay, so in my remaining time, I want to tell you what's different, like what's new challenges when you consider this L-shaped configuration instead of just corners.
So to be clear, your L-shaped configuration is just one leg in one direction and any number in other direction. Right?
In my theorem, it's a three-term
Okay,
direction.
I just said that it should work.
Yeah, it should like.
But the main restriction is in one direction. It's only one. In other words, when you make you're going to replace F, G, and H by, well, I'll watch.
Yeah, like 4 things.
Yeah, or more in general.
Yeah, so the this is basically like it's about as far as you can go and avoid this like weird approximate cohomology problem. basically the norms that control everything in this vertical direction are all it's morally like products of one-dimensional Gauss uniformity norms. But the thing that controls a like lonely thing, like in its own column, is one of these norms where you have to solve this approximate cohomology problem. But I can just kind of avoid it if I like I can treat the last term differently, but you can't in general treat multiple terms differently. Okay, so what's different for L-shaped configurations? Okay, so for corners, we saw that if you didn't have close to the random density of corners, then this was explained by your set having increased density on a product set. So for corners, we say that it turns out more general sets, but we skew for just normal product sets are the obstructions to uniformity. In that they explain like why your set doesn't behave like a random set. For L-shaped configurations, there are more and kind of more interesting obstructions to uniformity, and this is like the challenge to deal with these obstructions to uniformity. We get more for L-shapes. So in addition to kind of skew product sets and generalizations of those, you also get very general sets of the form, pairs X and Y, such that Y lies in some affine subspace that can vary with X. So for example, we'll consider the set pairs X and Y such that X dot Y is 0. Okay, so you can count the number of L-shaped configurations in this set. You get about P to the 3n over P cubed L-shapes. But this set has density around 1 over P. And the number of L-shapes that you would expect in a random set of density 1 over P is P to the 3n divided by P to the 4th. So this has many more than the expected number of L-shaped configurations. So another example is instead of taking X dot Y equals 0, you take here's X, Y, such that G of X dot Y is 0. We're now G of X is chosen uniformly at random from FP to the n. So even though we've introduced some randomness, this set still has density like 1 over P and around a factor of like P too many L-shaped configurations. So we have to deal with kind of these two different types of obstructions to uniformity for L-shaped configurations. Okay, so how does the proof go? So again, we study. Ooh, I don't know another letter. An average over L-shaped configurations, as we did for corners. And then we show that if S has no L shapes, then either this quantity, so you replace the in the weighted count, the first thing by F sub S, either this thing is large or something related to this is large. So just pretend we know that this is large. Okay, and now from this, we want to deduce a density increment on something. So it turns out that these sorts of averages are bounded by or controlled by some other norm, call it the star norm of F sub 0. And I'm not going to tell you what this is, but it's like a three-dimensional generalization of the box norm. It's not the three-dimensional box norm, but okay, I'm not going to write it down because it won't be enlightening. And then the basically understanding this norm is like part of the problem of like creating a like multi-dimensional version of higher order Fourier analysis. So then you want to show that if this norm of F sub S is large, you get a density increment. Show the star norm of F sub S is large implies the density increment not a product set, but a set of the form here is xy such that a of x times b of y. Oh, these are indicator functions. Times b of xy. A density increment on a set of this form, where phi is the set, basically a set of this form. So phi is phi of x dot m with y equals some element of fp that can depend on x. Okay, so now you would want to repeat the argument, but localized to a set of this form, just like we localized to a product set in Shkretov's proof. And for that, this, oh no, actually, for this, the analog of that inequality to hold, you need that A, B, and phi are sufficiently pseudo-random in some sense. So it turns out that the correct notion of pseudo-randomness is that A and B are pseudo-random with respect to the U10 norm on FP to that, and that phi is pseudo-random.
Then in your 42.
Yes, yeah, this is the culprit for the 42 trillion. And then you need that phi is pseudo-random with respect to the U8 norm. Now on FP to then cross FP to that. And then to do this, you need a version of the pseudo-randomization. Pseudo-randomization step needed after this. Okay, so I'll say, okay, what was the hard part of this argument? Because I've just made it look like the proof of the corners theorem. I'd say the hardest part was figuring out the correct pseudo-randomness hypothesis needed for phi. And this hypothesis that phi is pseudo-random with respect to the U8 norm doesn't directly translate to the sort of facts you need to prove that inequality. You actually have to do a lot of additive combinatorics, a lot of like proving results about like the combinatorics of approximate polynomials to show that this is like actually a good pseudorandomness condition. Because you also need a pseudorandomness condition that's amenable to one of these pseudorandomization, like energy increment type arguments. So I'd say like settling on this is actually the hardest part. Another difficult part is when you run this argument localized to a set of this form, or actually you localize it to a more complicated set. Proving that you actually get this density increment actually requires the transference principle, which was like the key ingredient of the proof of the Green-Tau theorem. Yeah, and then there's some technical things with the pseudorandomization step, but yeah, I won't be able to describe them to you. So I think I'll stop there.